Beyond the familiar orbits of our Sun's planets lies a realm of mystery and wonder, worlds that challenge our imagination and expand our understanding of what it means to be a planet. These are the exoplanets, planets that orbit stars other than our Sun, each one with its own story, its own secrets hidden in the light years between us and them. From scorching gas giants with atmospheres hotter than stars to frozen giants locked in eternal ice, these distant worlds offer a glimpse into the incredible diversity of planets that exist far beyond our solar system. As we journey through the cosmos, we will explore these planets, uncovering the extreme conditions, the strange orbits, and the profound mysteries that make them some of the most intriguing objects in the universe. WASP-12b and the concept of destruction. WASP-12b is a planet that captures the imagination not for its potential to harbor life, but for its dramatic, almost tragic existence. Located approximately 1,400 light-years from Earth, this exoplanet is on a slow path to oblivion. Its fate is sealed by its proximity to its parent star, a yellow dwarf that exerts a gravitational force so intense that it is gradually pulling the planet apart. WASP-12b's destruction is not an explosive event, but a drawn-out process, a reminder that in the universe, as in life, destruction can be as gradual as it is inevitable. WASP-12b is what scientists refer to as a hot Jupiter, a gas giant that orbits very close to its star. This proximity means that the planet is exposed to extreme levels of radiation and heat, with temperatures on its surface reaching over 2,500 degrees Celsius. Under such conditions, the atmosphere of WASP-12b is not just heated, it is being stripped away. The intense gravity of the star pulls on the planet's gaseous envelope, siphoning it off into space. Over time, this will lead to the complete disintegration of the planet, leaving behind nothing but a trail of gas and dust spiraling into the star. This slow, inexorable destruction raises profound questions about the nature of existence. WASP-12b is a cosmic symbol of impermanence, a reminder that in the vastness of the universe, nothing lasts forever. The planet's fate is a stark contrast to the images of creation and growth that often dominate our understanding of the cosmos. Instead of a world forming and flourishing, here we see one unraveling, a process that forces us to confront the reality that all things, no matter how grand or seemingly eternal, are subject to decay. The slow disintegration of WASP-12b can be seen as a metaphor for the human experience. Just as the planet is slowly pulled apart by forces beyond its control, so too are we shaped and ultimately undone by the forces of time. We are born, we grow, we live our lives, and eventually, we too must face our own end. The idea that our existence is fleeting is not new, but WASP-12b offers a striking, almost poetic illustration of this truth. It is a reminder that destruction is not always sudden or violent, but often a slow, creeping process that unfolds over time. Yet within this process of destruction, there is also a sense of transformation. As the material from WASP-12b is pulled into its star, it does not simply disappear. The gas and dust that once formed the planet will eventually be absorbed into the star, becoming part of it, fueling its energy, and contributing to the ongoing life of the star. In this way, WASP-12b's destruction is not an end, but a transition, a transformation from one form of existence to another. This idea of destruction leading to transformation has deep philosophical implications. It suggests that even in the face of total annihilation, there is the possibility of renewal, of something new emerging from the ashes of what was. In the same way, human life is marked by cycles of destruction and rebirth. We go through periods of loss and decay, but these are often followed by renewal, by the emergence of something new and different. It is a reminder that destruction is not the opposite of creation, but a part of it, a necessary step in the ongoing process of change and evolution. WASP-12b's fate also speaks to the fragility of existence. The planet, once a massive gas giant, is now being torn apart by the very star that once gave it life. This fragility is something we can all relate to. Our lives, too, are fragile, subject to forces beyond our control. We are shaped by our environments, by the people and circumstances that surround us, just as WASP-12b is shaped by the gravitational pull of its star. And like the planet, we are constantly in a state of change, constantly being shaped and reshaped by the forces around us. This fragility is not something to be feared, but rather something to be acknowledged and embraced. It is a reminder that life is precious, that every moment is fleeting and should be cherished. Just as WASP-12b is slowly being pulled apart, so too are we moving through the stages of our own lives, each moment bringing us closer to our own inevitable end. But within this fragility, there is also beauty, the beauty of existence, of experiencing life in all its forms, even as it slips away. The fate of WASP-12b also raises questions about the nature of endings. We often think of endings as final, as the point at which something ceases to exist. But WASP-12b challenges this notion. Its destruction is not a sudden event, but a gradual process, one that stretches out over time. In this way, the planet's end is not so much a single moment, but a series of moments, each one bringing it closer to its final dissolution. This challenges us to rethink our understanding of endings, to see them not as abrupt conclusions, but as transitions, as part of a larger process of change and transformation. In the end, the story of WASP-12b is a story of the universe itself, a universe that is constantly changing, constantly in a state of flux. It is a reminder that everything in the cosmos, from the smallest particle to the largest planet, is subject to the forces of time and change. The Enigma, GJ 1214b, and the Search for a Water World. GJ 1214b is a planet shrouded in mystery. Located about 48 light-years from Earth in the constellation Ophiuchus, this world has captured the imagination of scientists and astronomers since its discovery in 2009. GJ 1214b is often referred to as a super-Earth, a type of exoplanet that is larger than Earth but smaller than the gas giants like Neptune and Uranus. What makes GJ 1214b so intriguing is not just its size, but the thick, mysterious atmosphere that surrounds it. An atmosphere that has sparked countless theories and debates about what lies beneath its clouds. From the moment it was first observed, GJ 1214b has presented scientists with a puzzle. The planet orbits a red dwarf star, much smaller and cooler than our Sun, and it does so at a distance that places it in what could be a habitable zone, depending on the specifics of its atmosphere. However, what truly sets GJ 1214b apart is that its atmosphere is dense and opaque, making it nearly impossible to observe the planet's surface directly. This thick veil has led to a wealth of speculation about the nature of this distant world. One of the most compelling theories about GJ 1214b is that it could be a water world, a planet covered entirely by a deep global ocean. This idea stems from the planet's low density, which suggests that it is composed largely of water or other light materials, rather than rock or metal. If true, GJ 1214b could be a world unlike any other we have ever encountered, a planet where water is not just a feature of the landscape, but the defining characteristic of the entire world. The possibility of a water world raises many fascinating questions. Could life exist in such an environment? On Earth, water is a critical ingredient for life, and wherever we find water, we tend to find life as well. If GJ 1214b is indeed covered in a vast ocean, it might also harbor some form of life, perhaps in its deep, dark waters, shielded from the harsh conditions of space by the planet's thick atmosphere. But the challenges of studying such a distant and obscured world mean that these questions remain tantalizingly out of reach, at least for now. The mystery of GJ 1214b's atmosphere only deepens as scientists continue to study it. Early observations using the Hubble Space Telescope revealed that the planet's atmosphere might be rich in water vapor, further supporting the water world theory. However, the exact composition of the atmosphere remains unclear. Some models suggest that the atmosphere could be dominated by clouds of high-altitude steam, while others propose that it might be made up of more exotic materials, such as hydrogen or methane. Each of these possibilities would have profound implications for what lies beneath the clouds. If the atmosphere is indeed rich in water vapor, then GJ 1214b could be a steamy, hot world, with a thick layer of water vapor enveloping a deep ocean. But if the atmosphere is instead dominated by hydrogen, the planet could be more akin to a mini Neptune, with a thick gaseous envelope surrounding a rocky or icy core. Alternatively, if methane is the primary component, GJ 1214b might be a cold, distant cousin to the gas giants in our own solar system. Each scenario paints a very different picture of the planet, and yet the data so far has not been enough to definitively confirm or rule out any of these possibilities. The thick clouds that enshroud GJ 1214b have made it difficult for scientists to peer into the planet's depths. Most of what we know comes from indirect measurements, such as the way the planet's atmosphere absorbs and scatters light from its star. This has led to a sort of scientific detective work, where astronomers must piece together clues from various observations to build a coherent picture of the planet. It's a process that requires patience, creativity, and a willingness to embrace uncertainty, as each new observation seems to raise as many questions as it answers. One of the most intriguing aspects of GJ 1214b is the possibility that its atmosphere could be concealing something entirely unexpected. Planets like GJ 1214b, which fall into the category of super-Earths or mini-Neptunes, are relatively common in the galaxy, yet we know very little about them. This means that GJ 1214b could hold secrets that challenge our understanding of planet formation and evolution. For example, the planet could have a highly unusual internal structure, with layers of ice or rock that have been altered by the extreme pressures and temperatures within the planet. Alternatively, the atmosphere could be hiding chemical processes that we have never before observed on such a scale. The mystery of GJ 1214b has led to a number of imaginative theories about what might be happening beneath its clouds. Some scientists have speculated that the planet could have a thick supercritical water layer, a state of matter where water exists in a fluid form that is neither liquid nor gas, but something in between. In this scenario, the surface of GJ 1214b might be a strange alien environment where the distinction between sea and sky blurs into a continuous dense mist. Another theory suggests that GJ 1214b could be covered in a vast ocean of liquid ammonia or another exotic chemical rather than water. This would create an environment that is chemically and physically very different from anything we know on Earth. Life, if it existed in such an environment, would have to be radically different from any life forms we are familiar with, perhaps based on entirely different biochemistry. This possibility adds another layer of intrigue to the planet, as it forces us to reconsider the limits of life and the types of environments where it might thrive. The more we learn about GJ 1214b, the more enigmatic it becomes. Despite years of study, it remains one of the most puzzling exoplanets we have discovered. Each new observation brings us closer to understanding the planet, but also reveals new complexities that challenge our assumptions. It's a reminder that the universe is full of surprises, and that even the most well-studied objects can still hold secrets that defy easy explanation. The search for answers about GJ 1214b is ongoing, with scientists continuing to refine their models and develop new techniques for probing the planet's atmosphere. Future telescopes, like the James Webb Space Telescope, hold the promise of providing more detailed observations that could finally reveal the true nature of this mysterious world. But even as we edge closer to solving the puzzle of GJ 1214b, there is a sense that the planet will always retain some of its mystery, a distant, cloud-covered world that continues to fascinate and perplex us. GJ 1214b stands as a testament to the mysteries that lie beyond our solar system. It challenges us to think beyond what we know, to explore new possibilities, and to embrace the unknown. In the end, the search for answers about GJ 1214b is not just about understanding one distant planet. It's about pushing the boundaries of our knowledge and about the journey of discovery itself. The enigma of GJ 1214b reminds us that the universe is vast and full of wonders, and that there is always more to learn, more to explore, and more to discover. The Trappist One Family. The Trappist One system is one of the most intriguing discoveries in recent years, capturing the attention of scientists and the public alike. Located about 40 light-years from Earth in the constellation Aquarius, this star system is unlike anything we've seen before. What makes Trappist 1 so unique is its family of 7 Earth-sized planets, all orbiting a single, small star. These planets are packed closely together, with orbits much smaller than those in our solar system. And yet, despite their proximity to their parent star, several of them lie in what is known as the habitable zone, the region where conditions might be right for liquid water to exist. Trappist 1 itself is a cool dwarf star, much smaller and cooler than our Sun. Its planets, designated Trappist 1b through Trappist 1h, range in size and density, with some appearing to be rocky, much like Earth, while others might be covered in oceans or thick atmospheres. What makes this system so remarkable is the potential for these planets to host life. The discovery of so many Earth-sized worlds in one system, especially ones that might have the right conditions for life, has sparked a wave of excitement and curiosity within the scientific community. The orbits of the Trappist 1 planets are so tight that if you were standing on one, you could easily see the neighboring planets in the sky, perhaps even discern some of their surface features with the naked eye. The gravitational interactions between these closely packed planets are also fascinating. They influence each other's orbits in a delicate cosmic dance. This dance has allowed scientists to measure their masses with great precision, giving us more insight into their compositions and potential atmospheres. The discovery of the Trappist 1 system represents a significant leap forward in our understanding of the universe and our place within it. It challenges us to think beyond our solar system, to consider the possibilities of life in environments vastly different from our own. The fact that we found not just one, but 7 potentially habitable planets in a single star system suggests that such systems might be more common than we previously thought. This raises the tantalizing possibility that life could be abundant throughout the galaxy. Now, imagine if each of these 7 planets harbored completely different kinds of ecosystems, each shaped by the unique conditions of its environment. Trappist 1b, the closest planet to the star, might be a world of extremes, its surface scorched by the intense heat of the star. Perhaps it is a barren, rocky landscape, with rivers of molten rock and an atmosphere thick with vaporized minerals. Life, if it existed here, would need to be incredibly resilient, perhaps thriving underground, away from the searing heat, or in the shadowed craters where temperatures might be slightly more bearable. Further out, Trappist 1e sits comfortably in the habitable zone, where temperatures might allow for liquid water to exist on its surface. This planet might resemble Earth in many ways, with oceans, continents, and a breathable atmosphere. Imagine vast forests of alien trees, their leaves adapted to the dim red light of the Trappist 1 star. The seas might teem with life, from microscopic organisms to large, complex creatures that have evolved in a world where the day is almost as long as the year. Trappist 1f, slightly farther from the star, might be a world dominated by water, an ocean planet where the surface is completely covered by a deep global ocean. In this world, life could have evolved in the depths, far from the star's radiation, in an environment of perpetual darkness. Perhaps giant bioluminescent creatures swim through these dark waters, using light not only to see, but to communicate and attract mates. The ocean floor could be dotted with hydrothermal vents, providing the heat and nutrients needed to support a complex ecosystem. As we move outward, Trappist 1G might be a world of ice, its surface locked in eternal winter. But beneath this frozen crust, there could be a vast, subsurface ocean, kept liquid by the heat generated by tidal forces as the planet is pulled by the gravity of its star and neighboring planets. In this hidden ocean, life could exist in a completely different form, perhaps thriving around hydrothermal vents like on Trappist 1F, but adapted to a colder, darker environment. The creatures here might be slow-moving, conserving energy in a world where resources are scarce. Trappist 1H, the outermost planet, is likely a cold, icy world, far from the warmth of its star. Its atmosphere could be thin and its surface barren, much like Mars. But what if this planet had its own unique form of life, adapted to the cold and low gravity? Perhaps the surface is dotted with strange, hardy plants that capture and store the faint warmth of the star. Life here would need to be incredibly efficient, conserving every bit of energy and water it can find. The idea that each of the Trappist 1 planets could host its own distinct ecosystem is not just a flight of fancy, it's a reflection of the incredible diversity of life on Earth, where organisms have evolved to survive in some of the most extreme environments imaginable. From the scorching deserts to the icy polar regions, from the highest mountains to the deepest oceans. If life can thrive in such a wide range of conditions here on Earth, it's not so far-fetched to imagine that it could do the same on the Trappist 1 planets, given the right conditions. What makes this speculation so compelling is the sheer diversity that could exist within a single star system. While our solar system has only one planet in the habitable zone, Trappist 1 has 3 or 4. The possibilities for life, for ecosystems as varied and complex as those on Earth, are truly staggering. Each of these planets could represent a different chapter in the story of life in the universe, each one offering its own lessons, its own unique perspectives on what it means to be alive. The Trappist 1 system, with its 7 planets, invites us to expand our understanding of what life might look like elsewhere in the universe. It challenges us to think beyond our own experiences, to imagine ecosystems that are completely alien to us, shaped by conditions we can barely comprehend. Kepler 16b and its 2 suns. This exoplanet, located some 200 light-years away from Earth, orbits not 1, but 2 suns, a phenomenon that defies the familiar rhythm of our own solar system. Kepler 16b is often referred to as a circumbinary planet, a term that captures its unique relationship with 2 stars. These stars, affectionately named Kepler 16a and Kepler 16b, are locked in their own gravitational embrace, orbiting each other in a celestial dance that has persisted for billions of years. Kepler 16b, a giant of gas and rock, orbits this binary system with a precision that is both awe-inspiring and humbling. It moves in a stable, near-circular path, maintaining a delicate balance between the gravitational pulls of its twin suns, a feat of natural engineering that has captivated astronomers and dreamers alike. The concept of duality is central to understanding the significance of Kepler 16b's existence. In many ways, this distant world embodies the yin and yang of the universe, where opposing forces coexist in perfect equilibrium. The 2 suns of Kepler 16b are not identical. One is a bright sun-like star, while the other is a smaller, cooler red dwarf. Despite their differences, they work in concert, their combined gravitational forces creating a stable environment in which Kepler 16b can thrive. This planetary system reminds us that harmony does not require uniformity. Rather, it is often the interplay of contrasts that creates the most enduring balance. As Kepler 16b orbits its suns, it experiences a reality far removed from our own. Imagine standing on the surface of this planet where the sky is graced by not 1 but 2 blazing orbs of light. Depending on the time of day, both suns might shine together, casting dual shadows on the ground, or one might rise as the other sets, painting the sky in a kaleidoscope of colors. This is a world where twilight could stretch endlessly, as the stars dance around each other, their interplay of light and shadow creating a landscape that is both familiar and utterly alien. The duality of Kepler 16b's suns offers a rich metaphor for the complexities of existence. In the same way that this planet must navigate the gravitational pulls of two stars, so too must we navigate the opposing forces in our own lives. Light and dark, joy and sorrow, love and loss. These are the binaries that shape our existence, each pulling us in different directions, yet together forming the whole of our experience. Kepler 16b, with its twin suns, serves as a cosmic reminder that balance is not about choosing one side over the other, but about finding the point of equilibrium where both can coexist in harmony. In pondering the mysteries of Kepler 16b, one cannot help but wonder about the stories ancient civilizations might have told under such a sky. What myths would have arisen from the sight of two suns rising and setting in tandem, or from the eerie twilight that never truly ends? Perhaps they would have seen the dual suns as divine twins, representing the dual aspects of a single deity. One sun embodying creation, the other destruction, both essential to the cycle of life. Or maybe they would have envisioned the suns as lovers, forever chasing each other across the heavens, their dance a symbol of eternal passion and unending pursuit. In a world with two suns, the concept of time itself might have taken on new meanings. Days and nights would be governed not by the simple rising and setting of a single star, but by the complex interplay of two. Festivals might have been held when both suns were in the sky together, seen as a time of great power and possibility, or perhaps during the rare moments when one sun eclipsed the other, a moment of profound mystery and transformation. The sky, with its two guiding lights, would have been a canvas for endless imagination, a source of inspiration and wonder for generations. The inhabitants of such a world might have developed a philosophy centered around duality and balance, seeing in their two suns a reflection of the dualities that govern their own lives. They might have believed that just as their world was held in balance by the gravitational forces of two stars, so too were their own lives held in balance by the forces of good and evil, love and hate, joy and sorrow. The dance of the suns would have been seen as a cosmic lesson in the importance of finding harmony amidst the push and pull of opposing forces. The Diamond Planet, 55 Cancri E. 55 Cancri E is a planet that has captivated the imagination of scientists and the public alike, not just for its proximity to its star, but for the incredible possibility that it might be a planet made largely of diamond. Located 40 light-years away in the constellation Cancer, 55 Cancri E is a super-Earth, much larger and more massive than our own planet. It orbits extremely close to its parent star, completing a full revolution in just 18 hours. This close orbit means that 55 Cancri E experiences temperatures that reach over 2,400 degrees Celsius, conditions that are far too extreme for life as we know it. But it's not the heat or its proximity to its star that makes 55 Cancri E so intriguing. It's the composition of the planet itself. The idea that 55 Cancri E could be made largely of diamond comes from the planet's unusual density and the composition of its host star. The star, 55 Cancri A, has a much higher ratio of carbon to oxygen than our Sun, leading scientists to theorize that the planet could have formed in a carbon-rich environment. Under the intense pressure and heat within the planet, carbon could have crystallized into diamond, making 55 Cancri E a planet where the very bedrock is made of this precious gemstone. This possibility has sparked awe and speculation, leading to the nickname the Diamond Planet. It's a name that captures the imagination, evoking images of a world glittering with vast, unbroken expanses of diamond, shimmering under the light of its nearby star. The idea that an entire planet could be composed of diamond challenges our understanding of what is rare and valuable, pushing us to consider how we define wealth in a universe that is so vast and diverse. Diamonds on Earth are symbols of wealth, rarity, and beauty. They are formed deep within the Earth's mantle under extreme pressure and heat, then brought to the surface through volcanic eruptions. The process is rare, and the diamonds that result are treasured for their brilliance and hardness. But on 55 Cancri E, if the diamond planet theory is correct, diamonds might be as common as rocks are on Earth, making up a significant portion of the planet's structure. In such a place, the very idea of rarity is turned on its head. What is valuable in a world where diamonds are not rare, but commonplace? This question invites us to reflect on the nature of value itself. On Earth, the value of diamonds comes from their scarcity, their difficulty to obtain, and their beauty. But in a universe filled with unimaginable wonders, what does it mean for something to be precious? If diamonds were as common as dirt, would they still hold the same allure? Would we still treasure them, or would they become just another mundane part of the landscape? 55 Cancri E forces us to confront these questions, challenging our notions of wealth and rarity. It suggests that what we consider valuable is not an absolute measure, but something that is deeply contextual, shaped by the environment and the circumstances in which we find ourselves. On Earth, diamonds are rare and valuable because of the conditions that create them and the effort required to extract them. But on 55 Cancri E, those same conditions might be commonplace, making diamonds just another part of the planet's geology. This shift in perspective leads to a broader reflection on how we perceive value in the universe. The more we learn about the cosmos, the more we realize that what we consider extraordinary might be ordinary on a cosmic scale. There are planets made of diamond, stars that burn with unimaginable heat, and galaxies filled with billions of stars. In a universe so vast and diverse, how do we decide what is truly precious? Perhaps the answer lies in the way we experience these wonders. A diamond might be just a common rock on 55 Cancri E, but on Earth, it is a symbol of beauty and rarity because of the story it tells. The story of intense pressure and heat, of eons of time, and of the forces of nature that shape our world. In the same way, the value of anything, whether it is a diamond or a distant planet, comes from the meaning we ascribe to it, the stories we tell about it, and the ways it inspires us. The diamond planet also raises questions about our pursuit of material wealth. On Earth, much of human history has been driven by the quest for valuable resources, whether it is gold, oil, or diamonds. We have explored, mined, and fought over these materials, often with little regard for the consequences. But in a universe where planets like 55 Cancri E might exist, where entire worlds could be made of diamond, how do we reconcile our earthly desires with the vastness of the cosmos? This perspective encourages us to think beyond material wealth, to consider what truly matters in a universe that is so full of wonders. It challenges us to ask whether the pursuit of material riches is as meaningful as we often believe it to be, or whether there are other forms of wealth, knowledge, experience, connection that are even more valuable. In the end, the discovery of a planet like 55 Cancri E might lead us to a deeper understanding of what it means to be rich, not in terms of material possessions, but in terms of the experiences and insights that enrich our lives. The Dark World, Trappist 2b. Trappist 2b is a planet that challenges our expectations of what a world beyond our own should be. Discovered in 2006, this exoplanet orbits a star located about 750 light-years away in the constellation Draco. What sets Trappist 2b apart from the many other planets we've discovered is its astonishing darkness. It is one of the darkest known exoplanets, reflecting less than 1% of the light that hits it. In a universe filled with stars that burn brightly and planets that often reflect or glow with the light of their stars, Trappist 2b stands out as an anomaly. A world that seems to absorb almost all light, remaining shrouded in nearly complete darkness. Trappist 2b is a gas giant, similar in size and composition to Jupiter, but that is where the similarities end. Jupiter, with its swirling clouds and bright bands, is a planet that reflects a significant amount of the sunlight it receives. Trappist 2b, on the other hand, is so dark that if you were to look at it from space, it would appear as a black silhouette against the backdrop of its star, barely distinguishable from the void of space itself. The darkness of TRES 2b is so profound that it has been compared to the surface of charcoal or black acrylic paint. This planet does not shine, it does not sparkle. It lurks in the shadows, absorbing light, and offering little in return. The darkness of TRES 2b is more than just a physical characteristic. It evokes an emotional response that is hard to ignore. There is something unsettling about a world that is so completely dark, a world that seems to defy the natural order of things. In a universe where light is often associated with life, warmth, and energy, TRES 2b presents a stark contrast. It is a place where light goes to die, a planet that seems to embody the unknown and the fears that come with venturing into uncharted territories. The reasons behind TRES 2b's extreme darkness are still not fully understood, adding to the sense of mystery and unease that surrounds this planet. Scientists have speculated that the atmosphere of TRES 2b could be filled with chemicals that absorb light rather than reflect it. The planet's atmosphere might contain high levels of sodium, potassium, or titanium oxide, substances that are known to absorb light at certain wavelengths. Additionally, the extreme heat of the planet, which reaches temperatures of over 1,000 degrees Celsius, might prevent the formation of reflective clouds, leaving the atmosphere free to absorb light without scattering it. This combination of factors creates a world that is not only dark, but also hot, hostile, and uninviting. The atmosphere of TRES 2b is likely a swirling mix of gas and particles that trap heat, creating a broiling, suffocating environment. It is a planet that seems to repel life, a place where the conditions are so extreme that they challenge our understanding of what a planet can be. TRES 2b is not just dark. It is a world that feels fundamentally alien, a place where the rules that govern our familiar solar system do not seem to apply. The eerie nature of TRES 2b invites a deeper reflection on the unknown and on the fears that arise when we are confronted with something that defies our expectations. In many ways, TRES 2b serves as a metaphor for the darker aspects of exploration and discovery. It reminds us that the universe is vast and full of mysteries, and that not all of those mysteries are comforting or easy to understand. The darkness of TRES 2b is a physical reality, but it also represents the psychological darkness that comes with venturing into the unknown, the fear of what we might find, and the anxiety of confronting something that is completely outside our experience. There is a long history of darkness being associated with fear, danger, and the unknown. From ancient myths to modern horror stories, darkness has often been used as a symbol of the things that we cannot see or understand. TRES 2b taps into this deep-seated association, offering a tangible example of a world that is truly dark, not just in a physical sense, but in a way that challenges our sense of what is normal and safe. It is a reminder that the universe is not just full of light and warmth, but also of places that are cold, dark, and forbidding. Yet, despite the fear that such darkness can evoke, there is also a sense of awe and fascination. TRES 2b is a reminder that the universe is full of extremes, and that those extremes can be as compelling as they are unsettling. The very fact that a planet like TRES 2b exists pushes the boundaries of our understanding and forces us to confront the reality that the universe is far stranger and more complex than we often imagine. It challenges us to expand our horizons, to embrace the unknown, and to acknowledge that not all discoveries will be comforting or easy to understand. The Frozen Giant, Ogle 2005 BLG 390 LB, Ogle 2005 BLG 390 LB, or Ogle for short, is a planet that exists in the farthest reaches of the cold, a world so distant from its star that it remains locked in an eternal winter. Discovered in 2005, this exoplanet orbits a star located approximately 21,000 light-years away in the constellation Sagittarius. Its discovery was a remarkable feat, accomplished through a technique known as gravitational microlensing, where the planet's presence is inferred by the way its gravity bends the light of a more distant star as it passes in front of it. This method allowed astronomers to detect Ogul, even though it lies at such a vast distance from Earth, orbiting its star in a zone where the cold is so intense that it is almost unimaginable. Ogul is often referred to as a super-Earth, though it is very different from our own planet. It has a mass about 5 times that of Earth, making it larger, but not so large as to be classified as a gas giant. However, it is its location and the resulting conditions that truly set this planet apart. Ogul is situated far from its parent star, at a distance that places it well beyond the habitable zone where liquid water might exist. Instead, it resides in a region of space where the temperatures plummet to extreme lows, earning it the distinction of being one of the coldest known exoplanets. The temperature on Ogul is estimated to be around -220 degrees Celsius, a figure that is difficult to fully comprehend. At these temperatures, the planet's surface would be a frozen wasteland, a landscape where any atmosphere that might have once existed would be condensed into ice. Even the most resilient molecules would struggle to move, as the intense cold locks everything into a near-perfect stillness. This is a world where the cold is so deep and pervasive that it defines the very essence of the planet. The vast distance between Ogul and its star means that the planet receives only a tiny fraction of the light and heat that we experience on Earth. The star itself is likely a small, dim red dwarf, emitting only a faint glow that would barely reach the surface of the planet. Ogul exists in perpetual twilight, with its star appearing as little more than a distant dim point of light in the sky. The planet is bathed in darkness, its surface illuminated only by the feeble light of its distant sun and the occasional glimmer of far-off stars. The extreme cold of Ogul raises intriguing questions about the nature of such frozen worlds. What kind of landscape might exist on a planet where temperatures are so low? Would it be a place of endless plains of ice, stretching out in all directions? Or a world of jagged frozen mountains and deep ice-filled valleys? The lack of warmth would mean that any atmosphere or water that might have once existed would be frozen solid, creating a surface that is likely covered in thick layers of ice, possibly hundreds of kilometers deep. The idea of a frozen giant like Ogul also challenges our understanding of planetary formation and evolution. How does a planet end up so far from its star, in a region of space where the temperatures are so low? Did it form in this distant orbit, or was it once closer to its star, only to be flung outward by gravitational interactions with other planets or stars? These questions highlight the complexity and variety of planetary systems in the universe, reminding us that not all planets are like those in our solar system. The discovery of Ogul also invites us to consider the possibility of life in the most extreme environments. While the temperatures on this planet seem far too cold to support life as we know it, the universe is full of surprises, and life has proven to be remarkably adaptable in a wide range of environments. Could there be some form of life that thrives in the deep cold of Ogul, perhaps in the form of microorganisms that have evolved to survive in extreme conditions? While this seems unlikely, it is a question that pushes the boundaries of our understanding of life and its potential to exist in the most inhospitable places. The frozen surface of Ogul, with its unimaginable cold and its distant dim star, evokes a sense of isolation and desolation. This is a planet that exists at the edge of the possible, a world where the very concept of warmth and life is almost alien. It is a place that forces us to confront the limits of our knowledge and our imagination, as we try to picture a world so different from our own. The deep cold of Ogul serves as a reminder of the vastness of the universe and the incredible variety of worlds that exist within it. Yet, despite its extreme conditions, Ogul is a planet that is as much a part of the universe as Earth is. It exists in the same cosmos, governed by the same laws of physics and subject to the same forces of nature. Its discovery expands our understanding of what is possible, showing us that planets can exist in places we might never have thought to look, and that they can thrive in environments that seem utterly inhospitable. Ogul challenges us to think differently about what it means to be a planet. and what it means to exist in the universe. In contemplating Ojal, we are reminded of the incredible diversity of the cosmos. This frozen giant, locked in eternal winter, is just one of countless worlds that orbit the stars. HD 209458b, the first transit. HD 209458b, also known as Osiris, holds a special place in the history of astronomy. It was the first exoplanet ever observed transiting across the face of its star, an event that marked a significant milestone in our understanding of planets beyond our solar system. Located about 150 light-years away in the constellation Pegasus, Osiris is a gas giant, larger than Jupiter, and it orbits its star at a very close distance. This proximity to its star has resulted in some remarkable and extreme characteristics that have made Osiris a key object of study for astronomers. The discovery of Osiris was initially made through the detection of its gravitational influence on its parent star, a method known as the radial velocity technique. But the real breakthrough came when astronomers observed the planet passing directly in front of its star, a process known as a transit. This transit was first detected in 1999, and it allowed scientists to gather unprecedented data about the planet. For the first time, they could observe the dimming of the star's light as the planet passed in front of it, and from this they could infer the planet's size, mass, and even the composition of its atmosphere. Osiris orbits its star at a blistering pace, completing a full revolution in just over 3 days. This close orbit means that the planet is subject to extreme conditions, with temperatures soaring to around 1000 degrees Celsius. These high temperatures cause the planet's atmosphere to expand and become bloated, a phenomenon that has intrigued scientists since its discovery. The atmosphere of Osiris is so swollen that the planet's diameter is about 35% larger than that of Jupiter, despite having only about 70% of Jupiter's mass. The proximity to its star also means that Osiris is gradually losing its atmosphere. The intense radiation from the star heats the upper layers of the planet's atmosphere, causing them to expand and escape into space. This process, known as atmospheric escape, was one of the most striking discoveries made from observing Osiris's transit. It provided direct evidence that exoplanets could have dynamic atmospheres that are influenced by their environments, much like the planets in our own solar system. The study of Osiris was crucial in confirming the existence of atmospheres on exoplanets. Before its discovery, the idea that we could observe and analyze the atmosphere of a planet hundreds of light years away was purely theoretical. The transit of Osiris changed that, showing that not only could we detect these distant atmospheres, but we could also begin to study their composition and behavior in detail. Using spectroscopic techniques, astronomers were able to detect specific elements in the atmosphere of Osiris. They found signatures of hydrogen, oxygen, carbon, and sodium, among others. This was a groundbreaking discovery, as it was the first time that the composition of an exoplanet's atmosphere had been directly observed. It opened up a new field of study in astronomy, where scientists could begin to compare the atmospheres of different exoplanets, searching for similarities and differences that might reveal more about how these distant worlds formed and evolved. One of the most exciting findings from the study of Osiris's atmosphere was the detection of water vapor. While the temperatures on Osiris are far too high for liquid water to exist, the presence of water vapor suggested that the planet's atmosphere might be more complex than previously thought. This discovery raised the possibility that other exoplanets, particularly those in cooler orbits, might also have water in their atmospheres, potentially creating conditions more favorable for life. The significance of Osiris extends beyond just its atmosphere. The fact that it was the first transiting exoplanet meant that it became a template for how we study other exoplanets. The techniques developed to observe and analyze Osiris have since been applied to hundreds of other exoplanets, allowing astronomers to build a detailed understanding of the diversity of planets in our galaxy. The study of transits has become one of the most important methods for discovering and characterizing exoplanets, leading to the identification of thousands of planets, each with its own unique characteristics. Osiris also helped to confirm that many of the exoplanets we observe, particularly those close to their stars, are subject to extreme and often harsh conditions. The planet's bloated atmosphere and the loss of mass over time are direct consequences of its close orbit, highlighting the dynamic and sometimes violent nature of planetary systems. These findings have broadened our understanding of how planets interact with their stars and the potential long-term evolution of planetary atmospheres. The discovery and study of Osiris have had a profound impact on the field of exoplanet research. It showed that we could not only find planets beyond our solar system, but also study their atmospheres and learn about their physical properties in detail. This has led to the development of increasingly sophisticated techniques for studying exoplanets, from using ground-based telescopes to deploying space missions like the Hubble and James Webb Space Telescopes. These advances have brought us closer to answering fundamental questions about the nature of planets and the potential for life elsewhere in the universe. Osiris, as it is often called, is a planet that symbolizes the beginning of a new era in astronomy. It represents the moment when we began to move beyond just discovering exoplanets to truly studying them, learning about their atmospheres, their environments, and the forces that shape them. This gas giant, with its bloated atmosphere and its slow loss of mass, has taught us that the universe is full of planets that are as diverse as they are numerous. It has shown us that every planet has a story to tell, a story that can reveal more about the cosmos and our place within it. Kepler 186f, an Earth-sized planet in the habitable zone. Kepler 186f is a planet that has captivated both scientists and the public alike, not just because of its discovery, but because of what it represents in the ongoing search for life beyond Earth. Kepler 186f was discovered in 2014 by NASA's Kepler Space Telescope, a mission designed to find Earth-like planets orbiting other stars. The discovery was a monumental step forward in our quest to find planets that resemble our own, as it was the first Earth-sized planet found within the habitable zone of its star. This region, often referred to as the Goldilocks zone, is not too hot and not too cold, but just right for water to remain in a liquid state, assuming the planet has the right kind of atmosphere. The significance of this discovery cannot be overstated, as it brought us closer than ever before to finding a world that could potentially harbor life. Kepler 186f orbits a star that is much smaller and cooler than our Sun. This star, known as a red dwarf, is about half the size and mass of the Sun and emits less light. Because of this, Kepler 186f receives less energy from its star than Earth does from the Sun, leading scientists to speculate that the planet is likely cooler than Earth. However, the exact temperature on Kepler 186f depends heavily on the composition and thickness of its atmosphere, which remains unknown. If Kepler 186f has a thick atmosphere with a good amount of carbon dioxide or other greenhouse gases, it could trap enough heat to keep the planet warm, potentially allowing for liquid water to exist on its surface. The idea that Kepler 186f could support life is a tantalizing one. While we have yet to confirm the presence of water, an atmosphere, or any other signs of life, the planet's location within the habitable zone makes it one of the most promising candidates we've found so far. If Kepler 186f does have a stable atmosphere and liquid water, it could be home to a variety of life forms, ranging from simple microorganisms to more complex organisms, depending on the environmental conditions. The possibilities are vast, and they fuel our imagination as we consider what life might look like on a planet that, in many ways, could be a cousin to Earth. Kepler 186f is slightly larger than Earth, with a radius about 10% greater than our planet. This size difference, though small, suggests that Kepler 186f has a strong gravitational pull, which could help retain an atmosphere over billions of years. The planet's orbit around its star is also significant. Kepler 186f completes one orbit every 130 days, which means its year is shorter than an Earth year. However, because it orbits a cooler star, the planet receives just about the right amount of energy to keep it within the habitable zone, albeit on the outer edge of it. One of the challenges in studying Kepler 186f is the distance. At 500 light-years away, it is far beyond the reach of any current spacecraft, and even the most powerful telescopes struggle to provide detailed information about its surface conditions or atmosphere. However, scientists can still learn a great deal by studying the light from the planet's star as it passes through the planet's atmosphere during a transit. This technique, known as transmission spectroscopy, could reveal the composition of the planet's atmosphere, giving us clues about its potential to support life. The discovery of Kepler 186f has also prompted scientists to rethink the criteria for habitability. While the planet receives less energy than Earth, it is still within a range that might allow for liquid water, particularly if the planet has a dense atmosphere. This opens up the possibility that other planets, which might have been overlooked in the past because they were considered too cold, could also be habitable under the right conditions. Kepler 186f is a reminder that life might exist in places that are very different from Earth, but still within the bounds of what is physically possible. The significance of Kepler 186f extends beyond its potential for habitability. Its discovery has helped to confirm that Earth-sized planets are not rare in the galaxy, and that many of these planets may orbit within the habitable zones of their stars. This has profound implications for the search for life beyond our solar system. If planets like Kepler 186f are common, then the chances of finding a planet that harbors life increase dramatically. It suggests that the conditions that allowed life to arise on Earth might not be unique, and that there could be many other worlds where life has taken hold. Kepler 186f also represents a new era in the study of exoplanets, where we are not just finding planets, but finding planets that could be similar to Earth in crucial ways. The techniques and technologies developed to discover and study Kepler 186f have paved the way for future missions, such as the James Webb Space Telescope, which aims to provide even more detailed observations of exoplanets and their atmospheres. These missions will bring us closer to answering one of the most profound questions in science. Are we alone in the universe? While we still have much to learn about Kepler 186f, its discovery has inspired hope and curiosity. It reminds us that the universe is vast and full of possibilities, and that there may be other planets out there, waiting to be discovered, that could one day be homes to life. Kepler 186f is a symbol of the progress we have made in our search for other worlds, and of the exciting discoveries that lie ahead. A super-Earth in the habitable zone. HD 40307G or HDG is a fascinating exoplanet, often referred to as a super-Earth, a type of planet that is more massive than Earth, but smaller than the gas giants like Neptune and Uranus. Discovered in 2012, this planet orbits within the habitable zone of its star, a region where conditions might allow for liquid water to exist on its surface. Located about 42 light-years away from Earth in the constellation Pictor, HDG has captured the attention of astronomers and scientists, becoming a focal point in the ongoing search for potentially habitable worlds beyond our solar system. The star that HDG orbits, HD 40307, is a K-type dwarf star, smaller and cooler than our Sun. Despite being dimmer than our Sun, HD 40307 provides enough energy to its planets to create a habitable zone, where temperatures could be just right for liquid water, a critical ingredient for life as we know it. HDG lies comfortably within this zone, making it an intriguing candidate in the search for life beyond Earth. One of the defining features of HDG is its size. With a mass at least 7 times that of Earth, it is much larger than our planet, classifying it as a super-Earth. This increased mass suggests that HDG could have a significantly stronger gravitational pull than Earth, which would influence its atmosphere and surface conditions. The planet's larger size could mean a thicker atmosphere, possibly providing better insulation and protection from harmful cosmic radiation, making the environment more stable for potential life forms. HDG is part of a multi-planet system with at least 6 known planets orbiting the same star. This system is relatively close to Earth in astronomical terms, at just 42 light-years away. The proximity of HDG makes it a prime target for further study, as future telescopes might be able to provide more detailed observations of the planet and its atmosphere. The fact that HDG is in a multi-planet system also raises interesting questions about the dynamics of such systems and how planets in these environments interact with each other and their star. The potential for HDG to support liquid water makes it particularly interesting to scientists. The planet's position within the habitable zone means that if conditions are right, water could exist on its surface in liquid form. This possibility is crucial because liquid water is considered one of the most important factors in determining a planet's ability to support life. Water is not only a solvent that allows for chemical reactions, but it also plays a key role in regulating a planet's climate and supporting complex ecosystems. However, the exact conditions on HDG are still unknown. Much depends on the composition and thickness of the planet's atmosphere. If HDG has a dense atmosphere, it could trap enough heat to maintain liquid water on its surface, even though its star is cooler than the Sun. Conversely, if the atmosphere is too thin, the planet could be too cold for liquid water, despite being in the habitable zone. The composition of the atmosphere would also determine whether the planet has a stable climate and whether it could support life over long periods. The discovery of HDG has important implications for our understanding of planetary systems and the potential for life in the universe. Its existence confirms that super-Earths can form in the habitable zones of stars, and it suggests that there may be many more such planets waiting to be discovered. The fact that HDG orbits a star that is cooler and less massive than the Sun also expands the range of stars that could potentially host habitable planets. It shows that life-supporting planets might not be limited to systems like our own, but could be found around a wide variety of stars. HDG also represents a new frontier in the study of exoplanets. Its discovery has led to increased interest in the observation and characterization of super-Earths, particularly those in the habitable zones of their stars. These planets are of great interest because they could provide key insights into the conditions necessary for life and help us understand the diversity of planetary environments in the galaxy. The study of HDG and similar planets could also inform the search for life on other planets, guiding the development of future space missions and telescopes. In addition to its scientific importance, HDG has captured the imagination of the public and the scientific community alike. The idea of a planet similar to Earth, yet much larger, orbiting in a distant star system, is both intriguing and inspiring. It challenges us to think about what life might be like on such a world and what it would mean to discover signs of life on a planet that is so different from our own. The discovery of HDG reminds us that the universe is vast and full of possibilities, and that the search for life beyond Earth is just beginning. The continued study of HDG will likely involve a combination of observational techniques, including spectroscopy and direct imaging, to determine the composition of its atmosphere and surface conditions. Future missions, such as those planned for the James Webb Space Telescope, may be able to provide more detailed data about this fascinating planet, helping to answer some of the key questions about its potential to support life. As our technology improves and our understanding of exoplanets deepens, we may one day be able to determine whether HDG is truly a habitable world, or whether it is just another example of the incredible diversity of planets that exist in the universe. HDG is a reminder of the progress we have made in our understanding of exoplanets and the potential for life beyond Earth. It is a testament to the power of observation and discovery, and it shows us that there are still many mysteries to be uncovered in the universe. HD 106906b, a planetary outlier. HDB is a planet that defies many of the conventional ideas about how planets form and evolve. Located about 336 light-years away from Earth in the constellation Crux, this exoplanet is remarkable not just for its size, but for its extreme distance from its host star. HDB orbits its star at a distance that is 20 times farther than Neptune is from the Sun, placing it in an orbit that is both highly unusual and deeply intriguing to scientists. This planetary outlier, with a mass 11 times that of Jupiter, challenges our understanding of planetary systems and raises important questions about the processes that can lead to such distant orbits. The discovery of HDB was made in 2013, and from the beginning, it stood out as a puzzling and fascinating object. At such a great distance from its star, about 650 astronomical units, AU, where 1 AU is the distance from the Earth to the Sun, HDB is in a region of space where the gravitational influence of its star is relatively weak. In our own solar system, this distance would place the planet far beyond the Kuiper belt, in a zone where few objects are typically found and where planetary formation was not expected to occur. The sheer distance of HDB from its star has led scientists to reconsider the mechanisms by which planets can form and end up in such distant orbits. HDB is not only distant but also massive, with a mass that is 11 times that of Jupiter, making it one of the most massive exoplanets known. Its size and mass suggest that it is a gas giant, composed primarily of hydrogen and helium, much like Jupiter and Saturn in our own solar system. However, its location and orbit set it apart from these familiar giants. The wide orbit of HDB challenges traditional models of planetary formation, which typically involve planets forming within the protoplanetary disk of gas and dust that surrounds a young star. In these models, planets form relatively close to their stars, where the material needed to build them is most abundant. The presence of HDB in such a distant orbit suggests that it might have formed through a different process, or that it has undergone significant migration after its formation. One possibility is that HDB formed closer to its star and was later ejected into its current orbit through interactions with other massive objects in the system, such as a passing star or a massive planet. This scenario, known as gravitational scattering, could explain how the planet ended up so far from its star. However, such a process would likely result in a highly eccentric orbit, whereas HDB appears to have a relatively circular orbit, adding to the mystery. Another possibility is that HDB formed in isolation, far from its star, in a process more akin to the formation of brown dwarfs or even low-mass stars. In this scenario, the planet might have formed from the collapse of a separate cloud of gas and dust that was loosely associated with the star's system. This would mean that HDB is less of a planet in the traditional sense and more of a failed star, a substellar object that never accumulated enough mass to ignite nuclear fusion. If this is the case, HDB might represent a bridge between planets and brown dwarfs, objects that blur the line between the two categories. The unusual characteristics of HDB have made it a subject of intense study and interest within the scientific community. The planet challenges our understanding of how planetary systems form and evolve, suggesting that there may be more diversity in these processes than previously thought. It also raises questions about the stability and longevity of such distant orbits. Over time, interactions with other stars or the galactic environment could further perturb HDB's orbit, potentially leading to even more dramatic changes in its position relative to its star. The discovery of HDB has also prompted scientists to consider the implications for other planetary systems, including our own. If such distant and massive planets can exist in other systems, it raises the possibility that there may be similar objects in the far reaches of our solar system, beyond the Kuiper Belt and the known dwarf planets like Pluto. The ongoing search for Planet 9, a hypothetical large planet believed to be orbiting in the distant regions of our solar system, has been partly inspired by discoveries like HDB, which demonstrate that massive, distant planets can exist. The study of HDB and planets like it is not just about understanding one unusual world, but about expanding our knowledge of the range of possibilities for planetary systems as a whole. It challenges the notion that planets must fit neatly into the models we have developed based on our solar system, and shows that the universe is capable of producing planetary configurations that are far more diverse and complex than we might have imagined. HDB is a reminder that our understanding of the cosmos is still evolving, and that each new discovery has the potential to upend our existing theories and open up new avenues of exploration. In the years since its discovery, HDB has continued to be a focus of research, with astronomers using a variety of observational techniques to learn more about its orbit, composition, and possible history. Advances in technology, such as the upcoming James Webb Space Telescope, hold the promise of providing even more detailed observations of this distant planet, potentially revealing clues about its formation and the processes that govern its unusual orbit. These observations could help to answer some of the key questions about how HDB came to be where it is, and what it can tell us about the formation of other planetary systems. Kelt 9b, the hottest known exoplanet. Kelt 9b is a planet that exists at the extreme edge of what is possible, a world so hot that it challenges our very understanding of planetary environments. Discovered in 2017, this exoplanet is what astronomers refer to as an ultra-hot Jupiter, a gas giant that orbits its star so closely that its surface temperatures soar to unimaginable levels. Located about 670 light-years away from Earth in the constellation Cygnus, Kelt 9b is the hottest known exoplanet, with surface temperatures exceeding 4,000 degrees Celsius, 7,200 degrees Fahrenheit. This extreme heat puts it in a category all its own, making it a fascinating subject of study for scientists seeking to understand the limits of planetary conditions. Kelt 9b orbits a star known as Kelt 9, a hot, massive star that is itself much larger and hotter than our Sun. The planet's proximity to its star is staggering. Kelt 9b completes an orbit in just 1.5 days, which means it is extremely close to its star, far closer than Mercury is to the Sun. This tight orbit exposes Kelt 9b to intense radiation, which in turn drives its temperatures to some of the highest ever observed on any planet. The heat is so extreme that it rivals the temperatures of some stars, placing Kelt 9b in a league of its own when it comes to planetary environments. The conditions on Kelt 9b are unlike anything found in our solar system. The planet's atmosphere, composed mainly of hydrogen and helium, is heated to such high temperatures that the molecules within it are broken apart or dissociated into individual atoms. This process, known as thermal dissociation, occurs because the heat is so intense that chemical bonds simply cannot hold together. As a result, Kelt 9b's atmosphere is not just hot, but also chemically altered by the extreme conditions, creating an environment that is more like the outer layers of a star than a traditional planetary atmosphere. One of the most dramatic effects of this extreme heat is the way it causes Kelt 9b's atmosphere to be stripped away. The intense radiation from the star is constantly bombarding the planet, heating its atmosphere to the point where the outer layers begin to escape into space. This process creates a tail of escaping gas that streams behind the planet, similar to the tail of a comet. This tail is composed mainly of hydrogen, which is the lightest element and the most easily lost to space. The loss of atmospheric material is a striking visual reminder of the powerful forces at work on Kelt 9b, as the planet struggles to hold onto its atmosphere in the face of relentless radiation. The extreme conditions on Kelt 9b have made it a key target for scientific study particularly for understanding the effects of intense radiation on a planetary atmosphere. The planet provides a unique laboratory for studying how atmospheres behave under extreme heat, offering insights that could be applied to other hot Jupiters, or even to understanding the early atmospheres of rocky planets like Venus or Earth. By observing how Kelt 9b's atmosphere is stripped away and how its chemical composition is altered, scientists can learn more about the processes that shape planetary atmospheres in extreme environments. One of the key questions that Kelt 9b raises is how long a planet can survive in such an environment. The rate at which Kelt 9b is losing its atmosphere suggests that it is gradually being eroded away, though it is unclear how much material the planet is losing and how long this process has been ongoing. The planet's large size and massive gravity help it retain much of its atmosphere, but the intense radiation from its star means that this loss will continue as long as the planet remains in such a close orbit. This gradual erosion of the atmosphere is a process that can teach scientists a great deal about the long-term evolution of planets in extreme environments, particularly those that orbit close to hot, massive stars. Kelt 9b also provides an opportunity to study the interaction between a planet and its star in a very different context from our solar system. The extreme radiation from Kelt 9 means that the planet is constantly being bombarded with high-energy particles, which can have significant effects on the planet's atmosphere and magnetosphere. These interactions are important for understanding not just the physical characteristics of the planet, but also the potential for similar processes on other exoplanets that orbit close to their stars. The study of Kelt 9b is helping to build a broader understanding of how planets and stars interact, particularly in environments where the star's energy dominates the system. The discovery of Kelt 9b has also prompted scientists to think more broadly about the diversity of planetary environments in the universe. The extreme conditions on Kelt 9b show that planets can exist in environments that are far more hostile than anything found in our solar system, and that these planets can still retain atmospheres and exhibit complex behaviors. This has implications for our understanding of planetary formation and evolution, as it suggests that planets can form and survive in a wide range of environments, even those that seem inhospitable by earthly standards. Kelt 9b is also a reminder of the importance of observational technology in advancing our understanding of exoplanets. The planet was discovered using the Kilo-degree Extremely Little Telescope, KELT survey, a project designed to find transiting exoplanets around bright stars. The discovery of Kelt 9b was made possible by the precise measurements of the planet's transit across its star, which revealed the extreme conditions on this distant world. This underscores the importance of continued investment in telescopes and observational missions that can detect and study exoplanets in detail, particularly those that exist in extreme or unusual environments. As scientists continue to study Kelt 9b, they are likely to uncover even more about the planet's atmosphere, its interactions with its star, and the long-term fate of such an extreme world. The data collected from Kelt 9b will contribute to a growing body of knowledge about exoplanets, helping to refine models of planetary formation and evolution, and to understand the full range of conditions that planets can experience. Kelt 9b is a unique and valuable object of study, offering a glimpse into the extremes of planetary science and challenging our assumptions about what is possible in the universe. As we look to the future, Kelt 9b will likely continue to be a focus of research, particularly as new telescopes and instruments come online that can provide even more detailed observations of its atmosphere and its interactions with its star. The extreme conditions on Kelt 9b make it a fascinating object of study, and the insights gained from this planet will have implications for our understanding of exoplanets as a whole. Kelt 9b is a testament to the power of scientific discovery, showing that even in the most extreme environments, there is much to be learned and much to be explored. Feel free to subscribe if you enjoyed this video. Thank you for staying till the end.